Today we start learning about regression. We're going to spend several weeks on this. I want you to leave this class feeling quite comfortable with how to conduct a regression, how to understand it, report on it, interpret it, etc. So today we're going to talk about types of questions and cover why we use regression. We'll briefly mention some different types of regressions. Then we'll talk about setting up variables and then end with a couple of assumptions. So types of questions and types of regressions. I mentioned this when we talked about correlations and t-test, but it's very important at this point in the semester to kind of pause for a minute and ask ourselves, why are we doing all of this? When you're in the middle of recoding and merging, slicing, sorting, and cleaning data, it's easy to kind of lose track of what the whole purpose of all this is. But remember, we ask questions or we use data because we want to ask questions. We want to learn, we want to understand the world around us, and that's why we're doing all of this. So here's some example questions, and we used these examples when we talked about correlations and t-test. So for example, do children's grades differ by the city they live in? Do depression levels differ by sexual orientation? Now, the way I've phrased those questions, we'll mention in a second what types those are. You could also ask, how is marital satisfaction correlated with life satisfaction? And how is pro-social behavior correlated with social skills? So we use those examples when we talked about t-tests. Those first two and correlations. The first two there are very much independent sample t-test type of questions. So we could have two groups of sexual orientation and how do they differ on depression or depressive symptoms. We could have two groups with the cities that children live in and what are their grades like. Then those last two questions are very stereotypical correlation questions. How is this variable connected or correlated with this other one? Now, one of the reasons why we're spending so much time on regression here for the rest of the semester is that all four of those questions you could answer with regression. You don't have to use a different type of analysis. Regression can answer each of those. Now, before we talk more about why we use regression and where its real strengths are, I want to tie questions with code books. All right, we've spent a fair amount of time creating a code book with a midterm. We've used them with other in-class exercises, and we're going to use them throughout the rest of the semester. So it's fairly normal that when you have a question that you want to ask, that a data set will have multiple variables that you could use to answer that question. So a common question is, well, which variable should I use? And there's no like right answer here, in large part because it often is driven by your questions, what you're asking, and maybe some variables fit that just a little bit better. And sometimes you might do multiple models and analyses to help kind of answer that question. So let's say, for example, that I want to ask, how is sibling contact linked to well-being? That's a fairly general question. And as I look at this is a table of contents from a code book. Over here, I have a variable called contact with sibling. So I'm thinking of this as an independent variable. And so I need to use that one as my independent variable. That is what I have, that is contact with a sibling. But over here, I phrase this linked to well-being. That's fairly vague. And as you look through this code book, I think depressive symptoms, anxiety, general health, this is like physical health, life satisfaction, all of those could fit under well-being. So if the question is, well, which of those should I use? You'll want to just evaluate a little bit further. By well-being, do you mean physical well-being? Well, if that's the case, use general health. If by well-being you mean mental health, depression, or anxiety, or well-being you mean happiness, you should use life satisfaction. Or if you kind of mean all of those things, and you see those as being different facets of well-being, you might do a different model for each of those, or maybe for, two of them. So it's largely what variables you use are driven by your questions and what you're trying to answer. So if going back to 2 slides ago in those example questions, if we're able to use correlations and t-tests to answer some of these questions that we want to, why would we use regression, right? We've already learned how to do those two types of analyses. Why wouldn't we just spend more time getting better at those? Okay, So to help explain that, go with me on this kind of example here for a few minutes. Um, we're actually going to use this example quite a bit. We'll use it in some future videos as well. So let's imagine for a second that you are hypothesizing that children who go to high quality childcare centers, that they're going to have a larger vocabulary than children who go to low quality childcare centers. Seems like a fair hypothesis. So let's say you go and you collect data on this and you end up running a t-test. And sure enough, your t-test shows that the children who attend this high quality childcare center have a higher average vocabulary than the children who attend this lower quality childcare center. You could do a independent samples t-test for this. And you've got right then statistical evidence, and that's great. But it might be a little more complicated than that, because what might actually account for that mean difference that you're seeing? Or another way to say that is something else might account for that difference that you're seeing. For example, parents' education. Maybe parents who are more educated, maybe they are more likely to have a higher income, and maybe they send their kids to a higher quality childcare center. Okay, so maybe the parents' education is the real cause. Now, we tend to, in our field, want to avoid that word cause. Um, there's a whole discussion about that we could have. Ask me if you're interested. Um, but we tend to avoid that word, but I'm going to use it here anyways, right? So maybe it's parents' education is causing the vocabulary differences, not the actual childcare center. Or maybe it's about gender, sex. Maybe there are more girls at the higher quality childcare center just by happenstance. And maybe sex is actually accounting for that. Or maybe it really is that higher quality centers, maybe they actually do spend more time on education, talk more to the kids, do things that might help build vocabulary. So if we run a bunch of t-tests, we can't figure out which of those variables, whether it be parent education, sex, or the child center quality, we can't figure out which one of those is actually kind of causing, I know, right, using that word again, but causing or driving that effect that we're observing. So again, a t-test would be like, I'm going to do just these two variables and I'm going to ignore those two. And then I could do another t-test, right, between parent education and child vocabulary. And then I could do another one between sex and child vocabulary. But again, it doesn't help me figure out how those are all kind of connecting with each other. So this is where regression's really going to come in. Now, I do want to clarify something because I've used that word cause now a couple times. So in this case, I'm not saying that um, like parent education here is causing child sex. What we're saying is the real problem is that those three potential independent variables, sex, parent education, and child care center quality, that all of those might be correlated rather than them causing each other. And if we have these predictors or these independent variables that are correlated with one another, it causes a problem. Um, because if we just run t-test, we don't know which one is right, the one that really matters the most, or how they matter uniquely or in independent ways. So, kind of conceptually, what we're doing with regression then is we're taking all of those and we're running a bunch of t-tests at the same time in a way where the variables control for each other. So, when you hear the term we controlled for something, what you're saying is I accounted for the correlation between my independent variables. Or I, uh, there are some kind of challenging words that, at least for me, took me a while to understand when I started learning these concepts. But we partialed out the correlation between the independent variables. Accounted is probably a better word there. We accounted for the correlation so that we understood how each variable was linked to our dependent variable on its own or in its unique ways. Um, kind of a metaphor I like to use here is to think of it as pie. Partly this is where always my mind goes because I love pie, especially pumpkin pie. Um, and the idea is this pie represents our dependent variable. So in this case, vocabulary scores. And what we're going to do is we're going to say to each independent variable, which piece of this pie would you like to eat? Now, we don't cut it up yet, right? We just say, all right, child care center, which piece would you like to eat? And they say, oh, I would like to eat this part. And then we say to parent education, which part would you like to eat? And parent education says, I'll take that part. And then we ask sex, which part would you like to take? And sex says, I'll take this part. So what happens in regression is that any part where they overlap, we take that out, or we kind of set it to the side and we say, okay, the part that was unique, that sex wanted to eat or account for in our independent variable, or sorry, our dependent variable, in this case, vocabulary, that's where sex matters uniquely. We took out the parts where they overlap. This is where child care center mattered, and this is where parent education mattered. So we're able to look at the unique role of each variable after accounting for the other variables or controlling for them. This is why we call often variables control variables in a regression model. Okay, that's a really important concept. So if you're feeling uneasy about that, make sure you ask this in class so we can talk about it. All right, so this brings up then a couple of other points. The term R square. So when we run a regression model, one of the statistics we're going to get is called R square. And we'll actually start looking at R square next week and helping you understand that, the number, like what it actually means. But metaphorically, going with this idea of the pie, R square is how much of the pie all the variables eat. So there's potentially 100% of the pie. R square is interpreted as a percent of the pie that gets eaten by all of the independent variables. I've mentioned this now a couple of times, control variables. When we put a variable in the model, that counts as a control variable. Technically, independent variables and control variables are all the same thing. We usually just give that label independent variable to variables they're the ones that we're more interested in. They're the things we might be hypothesizing about. And I used that term a second ago about partialing things out. When we get to looking at our regression models, technically we are looking at correlations between our independent and our dependent variable, but we don't call them correlations because more specifically they're semi-partial correlations. Semi-partial correlation meaning it's not the entire correlation, it's only part of it. So if we've got, let's say, parent education here in the vocabulary variable. If I ran just the correlation between parent education and vocabulary, that is a correlation. But if I do it in a regression model, I am controlling for child center quality here and sex. And so my correlation now between parent education and vocabulary isn't the whole correlation, it's just it's a part of the correlation. That's where semi-partial comes in. All right, so types of regression. There are many types. We're only going to focus on one type. It's called multiple regression, and this is where we have one continuous or ordinal dependent variable, and we have one or more continuous, ordinal, or nominal independent variables. So we have at least one, but you typically have more than one independent variables. And dependent variable, that's our outcome, the thing we're trying to predict. Independent variables are the ones that are predicting those. Now there are synonyms for multiple regression, and there are more than this, but these are the most common. So linear regression, hierarchical regression, ordinary least squares regression, just sometimes simplified to OLS regression, and simple regression. Or even if people just say regression, they probably mean multiple regression. So there are other types of regressions that get more complex, other types of variables, but for us, we're going to focus here on multiple linear regression. Now, when we were working on correlations in t-test, I said to several of you that we were doing correlations in t-test because they're an important foundation for other things that we're going to be doing. And that's true, right? They're an important foundation for learning regression. But in many ways, regression is like the bicycle of statistical analyses. So you think about like learning to drive a car and um, just more complex types of vehicles. Having learned to ride a bike can be really helpful with that, helping you learn to navigate spaces while you're moving and stop and start and be aware of things around you. So regression is very much like that, in that it's a very important place to start when we're getting into more complex analyses. Regression is a complex of enough of analysis and rigorous enough that papers get published using regression all the time. It's a very normal type of analysis that you see in published research in many places. In fact, for the replication project, all of the articles, we chose those articles because they used regression. And since you're going to know how to do regression, you could attempt to duplicate their analysis. And to add to that, more complex things like structural equation modeling and multi-level modeling, they're all built on a regression foundation. So if you understand how to interpret a regression model, you're going to have a good sense then of how to interpret more complex statistical models too. All right, so that brings us then to setting up our variables. So this week we're calling this regression intro and prep. The prep part really comes from setting up our variables. And this is going to feel a little bit like stepping back to recoding, but it's a specific type of recoding that we need to do here to get ready for our analysis. Okay, so quick note here on terminology. Some of this is repeat, right? But repetition is super important here. So our dependent variable, sometimes this is called our outcome. This is the thing we're trying to predict. Um, so if I said, how is sibling contact linked to well-being? I'm thinking that well-being is my dependent variable here, because I'm assuming that sibling contact is kind of predicting, and even though we don't want to claim causality, kind of causing well-being. Independent variables are sometimes called predictors. These are all the variables that go into our model that we want to see how they're connected to that one dependent variable. And to say that again, it's you have in regression one dependent variable that has to be continuous or ordinal, and then one or more independent variables, and they can be continuous, ordinal, or nominal. And then control variables are technically independent variables too. And so everything that we cover about independent variables, it applies to our preparation of control variables too. Okay, so conceptually, as you're getting variables ready to use in your model, you want to keep your eye on the number 0. Now, on some level, I'm asking you to just trust me on this for now. We actually won't, it'll be another 2 weeks until that becomes more overtly apparent why. So I'm just asking you to trust me for now, right? And we'll get to that point. But said broadly, is that there's some of the statistics in our regression models that become more useful if we have a 0, a meaningful 0 in each of our independent and control variables. So to say that one other way, every independent variable in our regression models needs to have a meaningful 0. And just to clarify there, that's independent variables. So to kind of repeat this, this is often something that it takes a little time to get comfortable with. It's only the independent variables. Our dependent variables, we leave them as they are. They don't need to have a meaningful 0. In fact, you don't want to make them have a meaningful 0 if they don't naturally have one. So what do I mean then by a meaningful 0? With continuous and ordinal variables, that means we're going to do something called centering them. That means we're going to change the scale so that it includes a 0. Now, the first time I learned about this, I thought, that's weird. This feels like messing with the data. Like this almost feels inappropriate. I promise you it is not inappropriate. In fact, it's completely appropriate, something that we should do. So let's imagine you've got a scale, a 1 to 5 scale. Right, we've asked people over the last week, how sad were you on a 1 to 5 scale? We want to have a 0 there, but there isn't one to begin with. Or let's say we've measured people's ages and we're doing a study on adolescents. So we have 12 to 18-year-olds. Well, none of them are 0, and that's problematic. It's not problematic that we don't have any 12 to 18-year-olds, but it's problematic that we don't have a 0 on that scale. So what are we going to do? What we're going to do is we're going to center them. The most common method for doing this is doing what's called mean centering. So let's imagine on that 1 to 5 scale, we collect all of our data, and after we've collected it all, the average or the mean on that scale is a 3. So what we're going to do is we're going to subtract a 3 from everybody's score. So now instead of having 1, 2, 3, 4, 5, I have -2, -1, 0, 1, and 2. So it's still a 5-point scale. All I've done is I've just slid things down so that now we have a 0. The great thing about that is it doesn't change the way it's correlated with other variables. So this is why it's completely an okay thing to do, is because it doesn't really change mathematically how that variable is used, but it's going to change some of the information that the regression model is going to give us. Going with that example of 12 to 18, so let's say our average is 15.45. All we're going to do is subtract the mean. And so anybody who is a 12 is now going to be a -3.45. Anybody who's 17 is now 1.55. And this feels kind of weird, but all of these ages are still, like, they have the same difference as they did before. I'm thinking some of these numbers I typed wrong. Those should actually be 0.55. Yeah, 0.55 and 3.55. I typed those in wrong. But the point is, right, we can change it so that now the scale encompasses 0. And in this case, you might say, well, there are no zeros on there. And more, it's the point that you encompass 0. So in this case, now, way too far. There we go. In this example, right, if they were all whole numbers, yes, some people will actually be coded 0. But the more point is that we encompass 0 now on our scale. So in this case, we have negative numbers and we have positive numbers, so 0 is encompassed. Now, the basic kind of code for this is you're going to create a new variable, do into, and take the original variable and subtract from it the mean. Don't copy that code though. This code right here is going to be a whole lot better. So I'm specifying the data frame, money symbol, and then a variable. And I like to use the same variable name as the original one, but I like to put a C on the end. C is just a common notation to mean this has been centered. So same name and then just a C on the end of it. So then I do into data frame money symbol, the original variable, and I subtract from that and I do the function mean, data frame, money symbol, and the variable name. And then this option na.rm mean equals true. So I'm saying if there are any missing values, just skip over those. All right, so we're going to jump over now to RStudio. All right, so I've created a data frame here. It's a fake data frame called vocab. I'm going to go ahead and I've already set my working directory. Got the code to bring the data in. Let's go ahead and look at that. So this is a completely fake data frame. It's got a little bit of missing data here and there. We have a variable called child vocab. So this is children's vocabulary scores. We have their sex. We have center quality, which means the quality of the child care center they attend, their parents' education level, and their ethnicity. If we scroll down a little bit in the script here, I've got a code book that I've typed in that explains each of those variables a little bit more. Now remember, all the code when I'm making these videos, you can find this code on Learning Suite under content and under the video page for this material. So it's helpful to download this. You can copy this code into your own for the cheat sheet. And it's also helpful just to work through the exercises also as I'm doing it here. All right, so mean centering, continuous, ordinal. I'm going to use that notation IVs, meaning independent variables. Remember, we don't center dependent variables, and you don't mean center nominal variables. It's only continuous and ordinal variables. Let's put a note here. Okay. All right, so we got this child vocab and center quality and parent education. These are all continuous and ordinal variables on a 1 to 7 scale. But we're going to go with that question we asked in PowerPoint about predicting children's vocabulary scores. So this is going to end up being our dependent variable. So we're not going to mean center it, but we're going to mean center quality and parent education. So the data set is called vocab. Do money symbol. Let's do center quality first. We're going to put a C on the end of that. And then I'm going to just copy that original variable and subtract from it the mean and put in again that variable, so it's going to subtract mean. Now I'm going to run that, and oh, it did work. Sometimes I'm like, oh, I'm going to really demonstrate. Oh, it's on parent education. No, there is one there. Oh, here we go. Yeah, it did what I was hoping it was doing. Then we're going to run describe, and we're going to actually run describe on both variables because I want to highlight something here. But what I do is run describe on both variables to use it to verify. So verify that we did things correctly. So let's run describe on the original variable, the uncentered version. So our mean is 5.71. We had 692 people in our sample. It means we had a little bit of missing data. You got skew and kurtosis, minimum and maximum. So then I'm going to run it on the new variable, and we've got an error here. It says no non-missing arguments to min, returning infinity. Essentially, right, there's some missing data in here, and if we look at this, it's like that doesn't work. The reason for that is that when we had it subtract the mean, because there's some missing data in this data set, we can see some of it if we just kind of scroll through. There's an NA on center quality. It's going to make it so it couldn't calculate that mean. That's why we need to do that option na.rm equals true. So if I run that now, and we go look at it, now we've got values. But we need to verify. Let me just type here what we're looking for. Okay, so let's look at the original variable again and then the one that we just centered. So the original variable had a standard deviation of 5.71, excuse me. And so all we did was just from everybody's score was subtract 5.71. So our mean should now be 0, and sure enough it is. But our standard deviation should not change. It should stay the same. So we've still got 1.13. Things like our skew and kurtosis also won't change. So that's what I'm looking for to verify. Now my min and my max, that's going to change. My mean is going to change, but my standard deviation, my skew and kurtosis are not going to change. And in this case, they didn't, so we know that worked. Let's do it on parent education. I'm just going to copy that code. We're going to change the variable here to parent education. And I'm just copying and pasting. So I'm just like double click on that variable It highlights it, and then I can paste over the top of it. And then I'm going to add the C on those two. And let's run all of that. So in the original parent education variable, we had a mean of 5.89. Now we have a mean of 0. Check. That looks good. We originally had a standard deviation of 0.96, and on the new variable, we have a standard deviation of 0.96. Check. That worked great. So that's all there is to mean centering variables. And those two are now ready to be used in a regression model. Okay, so that's continuous and ordinal variables. But what if we have nominal variables? How are we going to use those? The process here is initially going to feel different depending on how many groups or levels there are to the nominal variable. But the truth is it's actually the same. But even though it's technically the same, we're going to talk about first variables that have two levels, nominal variables meaning two groups, and those that have more than two. Okay, so for two-level nominal variables, like let's say you have a sex variable and you only have male or female, or you have an ethnicity variable, minority versus not minority, or graduated versus not graduated. You've just got two groups. In those cases, what we want to do is make one of the categories 0 and the other 1. Now you might have noticed that in most cases, in fact I think there was only one exception in the code book for the midterm, I wanted you to code these two-level nominal variables as 0s and 1s. That's just a good habit to do in your regular data cleaning so that it's ready for your analysis and you don't have to do anything else to it. So if I had a sex variable, I might code males as 1 and females as 0, minorities as 1, non-minorities as 0. And again, just to say that one more time, I do this when I'm cleaning data. So all my two-level nominal variables should be ready to go. Now, there's kind of some common naming conventions when it comes to these two-level nominal variables. So a common practice here is if I have a variable and I call it male, that should mean that male is the group that is coded as 1 and the other group is coded as a 0. Or if I name a variable student, then student would be coded as a 1. Everybody else, meaning not a student, would be coded as a 0. Not everybody does that, but it is a common naming convention that you see in a lot of places. All right, let's talk about, or jump over to RStudio and do this. All right. Prepping a two-level nominal variable. So in this little data set, we have child sex. Male is 1, female is 2. So let's create a new variable and let's call it female. So vocab female, and we're going to take it from the original variable. It's called child sex. And this one's actually pretty simple, right? So originally it's a 1 and a 2. So if I'm going to call the variable female, I can just subtract a 1 from each case. So everybody who's a male will now become 0, and everybody who's a female will now become 1. When I'm doing this type of thing, I love to put a little thing in my script here about how it was coded, just in case there's any confusion down the road. And if you remember from all of our recoding practice, we do want to run table here and make sure that worked. So on the original variable, everybody who was a 2 is now a 1. Everybody who is a 1 is now a 0. Now that's pretty simple when you can just subtract like that. You do know how to recode. You're all very good at it at this point. But let's just go over this in case. So if I wanted to create a variable called male, what we did was, well, you'll notice something here, right? I'm not rewriting over that child's sex variable. I'm leaving it as it is. When I'm doing this type of prepping with nominal variables, that's a good practice to not rewrite over the original. We did when we were cleaning the data because we wanted that final version in the code book. But in the case like this where you've got a data set and the code book already has this child sex variable, I don't want to delete the child sex variable out of the code book or replace it with this new coding because it then won't match the code book. So that's why I'm giving it a new name so that it's something different than what was originally in the code book. And that just helps you avoid confusion. Otherwise, somebody, right, is maybe working on your script later. They come in and be like, oh, they've got child sex in there. It's coded as a 1 and a 2, but you've changed it to a 0 and a 1. And without careful look at your data or your script, they may not see that. So if I wanted to instead create one called male, what I could do is do brackets here and say if child sex equals 2, oh, this is actually going to feel a bit silly, but if child sex equals 1, code male is 1, and if child sex equals 2, code it as 0, and then put a little note here at the end of my script, say something like that. And again, you need to verify that. It is so easy to make mistakes when you're doing this type of thing. So again, just to walk this through, so I'm saying code a variable called male, and if child sex equals 1, then I want to code male as 1. On that new variable male, if child sex equals 2, I want you to code the new one as 0. And then we can just run that, make sure it worked, and sure enough, everybody who was a 2 is now a 0, and everybody who was a 1 is still a 1. So 2-level variables, super easy. Okay, so what about more complex? So you've got 3 or more groups or levels in a nominal variable. How are we going to use those? And this is, highlighting also a reason why regression becomes really useful, because if you remember right with independent samples t-test, we couldn't use nominal variables that had more than 2 groups. But with regression, we can. So that's a place where this becomes a lot more powerful. So if you've got, let's say, ethnicity in multiple categories, or marital status in multiple categories, or favorite type of food, or favorite sport, those kind of things, or university attended, etc. So what we're going to do is we're going to create something called dummy codes. And I admit, for a while I was like, dummy codes? When I say a while, years. I always just thought that was a really weird name. But one day just kind of had this epiphany. So I served my mission in Northern England, and in the UK, and I don't know, if this is true in Ireland actually, or Northern Ireland, but it is at least in England and Wales that a pacifier is called a dummy. And that's, I think, the reason why these are called dummy codes. And I'm going to circle back to in a second again, and make that connection, because at this point it doesn't. But just remember, a dummy is something that helps children be quiet, like a pacifier. So dummy codes. What we're going to do is we're going to create a new variable for each level of that original variable. But we're only going to end up using some of those in our model. Okay, so to say this one more time, you're going to create a new variable for each level or each group of that original nominal variable. Okay, so let's go with this example of marital status. So let's say I ask their marital status and I've got these 5 potential groups. Are you married? Are you divorced? Are you widowed, never married, or remarried? So what I'm going to do is I'm going to create then 5 new variables down here. And what I'm going to do is I'm going to name that first one married. I'm naming it what that group corresponds to. And if anybody was coded as a 1 on that original married variable, I'm going to code them as a 1 on the new variable. Hopefully that kind of makes sense how you would do this. Now we're going to do this in a second, but right, you've got brackets. You've got your new variable married brackets if old marital status variable equals 1 into 1. Now if they were a 2 on that original variable, I'm going to code them a 0 on that married variable. And for widowed, never married, remarried, all of those people are going to get coded a 0 on that married variable. Now, this goes back to what we were just saying about like the male and the female variable. So this variable, everybody who is a 1 is coded a 1, and everybody else is 0. Then we're going to create a variable called divorced, and it's going to follow that same pattern, but the number's slightly different, right? So everybody who was a divorced or scored a 2 on that original marital status variable, we're going to code them a 1. And everybody else, the married, widowed, never married, and remarried, they're all going to get coded a 0. That's because this variable is called divorced. And so 1 means divorced, and everybody, all the other zeros means not divorced. Then we just keep going down that line. So create a new variable called widowed. Everybody who was widowed or scored a 3 on that original one, they're going to be coded a 1. And everybody else, meaning the married, divorced, never married, and remarried, they're all going to be coded a 0. And then I'm going to create a variable called never married and follow that same pattern, and one called remarried. So I'm ending up here with 5 new variables because I had 5 groups and that original marital status variable. So to repeat myself, we're not going to end up using all 5 of those variables, but I want you to just go ahead and create them anyways. It's just a lot simpler process to just go ahead and create them too. Okay, now another kind of consideration here, when we are running our independent samples t-test, we said that it was good to have at least 30 people in each group. That applies here too. And this often becomes a little trickier when we've got bigger groups or a variable with more groups, because sometimes you don't have very many people in like one of the groups. So it's fairly common to see in studies where they're going to end up condensing, and they'll say like married or not married, minority versus non-minority. And the reason we often do that is maybe we don't have enough people in each group to create all of these dummy codes. So to say that again, you want to have at least really 30 people in each group if they're going to be made into their own dummy code. If there isn't, you need some kind of logical way of how you might combine those. So let's jump back to this example here really quick. Let's just say, we didn't have very many people in the widowed and remarried category, but all the others did. I might then classify this as something like the ever married, right? So the things that the married, divorced, widowed, and remarried groups all share is that they have been married at some point. Or if the remarried group was the one where you didn't have very many people there, I might say like currently married and make the married and the remarried into one variable, and then have divorced, widowed, and never married be their own variables. Or I might just simply say currently married, not married, and simplify it into 2 groups rather than having 5. So you want to run some descriptive stats here first. Make sure you know what you're working with. Make some decisions before you just go ahead and make all 5 of those groups. So like in this example, if we only had 15 people in group 4 and 3 here, those are going to need to be grouped with one of these other groups in some way that makes sense. Just always make sure that it makes logical sense. So let's jump over back to our studio and look at prepping nominal variables with 3 plus groups / levels. Okay. All right, so if we come back up here, the variable we've got here is ethnicity. And really what we want to do, going on that idea, right, of making sure you have enough people in each group, let's look at our data here first. Okay, so 1 is black, 2 is Hispanic, 3 is other, and 4 is white. So we have at least 30 people in each group. It looks to me like we're going to be okay there. You know, if we had less than 30 in this group, we might do minority, other, and white, right, and have 3 groups instead of 4. All right, but we have enough, so we're going to do 4 groups. So, okay, so now recode a new variable for each group. Copy and paste here is going to be, as always, your best friend. So let's create one called black, and we're going to do brackets and say if ethnicity equals 1, and code into a1. And then I'm going to copy that 4 times, and I'm going to just change those to 1, 2, 3, 4, and then all these others get coded as zeros. So everybody who is a 1 on the ethnicity variable is now going to get coded as a 1 on the black variable, and everybody else is going to get coded a 0. Then at the end, we're going to verify that. So we're going to do table and do these crosstabs and verify that. Now, error, all arguments must have the same length. I didn't actually run the data or the code. And always, sometimes I'm like, what? I just coded that. Why didn't it work? Well, you didn't run the code. Of course it didn't work. So everybody who was a 1 on the old variable is still a 1. Everybody who's a 2, 3, or 4 is now a 0 on that new variable. That's exactly what we're looking for. So then I'm going to go ahead and do that for each group. So I'm going to copy and paste that section of code 4 times because I have 4 groups. And then I'm going to change the names. What was a 2 on the other one? Hispanic. And on the Hispanic variable, everybody who has a 2 is a 1, and everybody else is a 0. So I'm just trying to make really good use here of copy and paste. Again, if I double click on a variable name, it will highlight it, so I can just replace it. And I think our last one is white. Now, verifying is always very important, but when you're using a lot of copy and paste like this, verifying becomes even more important. So we already verified the black one, Hispanic. Yes. If they were 2, they're 1. Everybody else is a 0. For other, they're all a 1. If they were a 3, everybody else is a 0. And on white, if they were a 4, they're now 1. Everybody else is a 0. Okay. That's it. So now we've got those variables. They are ready to use. And we're not covering yet how to use them. In our model, we're just preparing to get them ready for use. All right. So that brings us then to our last topic here with regression is assumptions. Now, assumptions, right, in life can be a bad thing, but in statistics, they're really important. And as we talked about with t-test, assumptions often form kind of this foundation, things that are needed for a model to work correctly. So we're going to hit just 3 of these that are important. So the first one here is we want to have at least 20 cases per independent variable. So if I have 5 independent variables in my model, that means that I could use, or I need to have at least 100 people in my sample, or 100 cases in my sample, or 100 rows, all of those being synonyms. If I want to use 10 independent or control variables, then I need to have 200 cases or 200 rows. And when you're working with smaller data sets, particularly with nonprofits, you want to pay really close attention to that. And sometimes you've got to make some hard decisions as to what variables you're going to use, because you can't just include anything that you might possibly want to include. The next is, and we've said this a couple times, but really, and hammering this home, is that you need to have continuous or ordinal outcomes, meaning your dependent variables. Now, I admit, I can put an exclamation point there, right? Nominal outcomes won't work at all. If I'm being completely honest, that's not 100% true. There's some disciplines that would say that's not even a thing, but there are better regression models when you have a nominal outcome. And there's just some enough complexity there that for our class, we're going to say at this point, nominal variables cannot be used as dependent variables. If you find yourself in a position later on, and you haven't taken more advanced stats classes where you've learned how to do what's called logistic regression, um, look it up. After you've learned regression, it's not a terribly big leap or step to use it. It's just enough that we don't have time in this class to cover it. One of my dreams in life is that we get to turn this into 2 classes. So the first half is data cleaning and the second half is analysis. Someday, if that dream ever happens, we'll cover logistic regression. The other one is independence. And this is a simple fix if we violate this, very much like the equal variance test with our independent samples t-test. We just adjust our code if our data violates this assumption. So the assumption in regression is that any participant on a row of data is no more like systematically similar to another participant than any other participant. So if I compare, participant 1 to participant 89, there's nothing systematic that necessarily makes participant 1 and 89 more similar than participant 1 and participant 80, 326 would be. So in this case, if I sampled one parent from each family, that's fine, right? There's nothing about this mother that's more similar to this father than she is to this mother necessarily. So there's no problem. But instead, if I, let's say, sample husbands and wives from different families, but I get husbands and wives also from the same family. Now, his responses, say, on an easy example on marital satisfaction, are probably more similar to hers than they would systematically be to these other people because they're in a relationship with each other. So we call that the data are not independent. So here, their responses are independent of one another's in some systematic way. But these ones have a systematic way to where their responses might be more similar than they would be to any other person. So some really common ways that this is violated is if, again, you've got more than one person per household. So for myself, I run into this fairly regularly. I study sibling relationships. And if I'm going to measure multiple siblings from the same family, guess what? Right? Siblings are more likely to be similar to each other than they are a random stranger. So I violated this assumption. An even more common way than that is having students in a classroom. Excuse me, a classroom. So if we were going to measure, actually, a good example of this, almost a decade ago, my older brother uh, did a study where he was looking at BYU students' successes in the classroom, and kind of their growth in terms of the aims of a BYU education. And so he recruited professors who then would recruit their students. So Professor A, so I was a participant in his study, I had, 30, 60 students from my class participate. But then somebody else in the department participated, and they had 30 or 60 students. So their 30 or 60 students were more similar to each other in terms of their experience in that semester because they were in that classroom together, and the ones who were in my classroom would be more similar in their experience because they were in my classroom. Um, Sometimes we use the term saying those are nested. So you have kids or students nested within classrooms, or people nested within families, or within couples. You could have this in the business world too, if you have multiple employees from the same office, and then you have multiple offices. Okay, so just a couple more things on this, right? So this is only a problem if your participants are from the same group and not other groups. So, right, it's okay to have people from families as long as you don't have multiple people from the same families. Um, so going with the classroom example, right? Or if you only have people, sorry, I'm saying that not quite the right way I intended. It's not a problem if you only have people from one group. So if we did a study, and we only looked at those in our classroom, that's fine. But as soon as we include other classrooms, now we're violating that assumption. Theoretically, I could look at people from just one family, not a problem. But as soon as I have multiple families and multiple people from each family, now I've got a problem. So what do we do here? Well, first is you don't ignore it. And I'm not going to put this code into Learning Suite, but this is the code that you would need. The biggest thing is LM is the function for regression. Instead, we're just changing it to LM cluster. This is all the same regression code that we'd normally do. And then all you're doing is you're adding cluster and you're adding this grouping variable. Grouping variable here is like an ID variable for families or for classrooms. It's the variable that you have people within. So families here is the easiest example. So if I have, in fact, you've done this. So let's say you've got a data set that has multiple siblings, and you change that data set so that you have one person on each line. You've got the older sibling on one line and the younger sibling on its own line. But they both share the same family ID variable. That family ID variable goes here. So a common question then is, well, how do I know if I've violated this assumption? And really, it's just understanding how your data are structured. So you just need to ask yourself, do I have things like families or classrooms in my data set? Okay, if I do I have multiple rows for people within that data set or within those groups? So if I have lots of families, and yes, I surveyed moms and dads, but moms and dads are on the same row of data, it's okay. It's as soon as I put dads on their own row of data and moms on their own row of data that now I've got a problem. Okay, so let me say one last thing about assumptions. There are other assumptions, and ones that are important, but we didn't cover them here for two reasons. One being is that we're going to be covering enough hard things with regression that sometimes we don't get the absolute critical foundations if we focus on the other assumptions. And two is they're ones that often are not a problem. They occasionally are, but often are not. So this is just my way of saying, right, you land yourself in a future position or job where you're using regression a lot. I would encourage you to read up a little bit more on these other assumptions. The other ones that we're not covering, there are tests for. There are things like homoscedasticity, um, and normality of residuals, and some things like that. So, okay, that's it for prepping regression, and we will see you in class.